Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Welcome, this is Mr. Simon, and we are here to change our world with chemistry. So we are on unit number 12, still talking about conductivity of solutions, and today we are going to actually talk about the factors affecting molar conductivity. Who remembers the definition of molar conductivity? Yeah, thank you very much. Thank you very much. But last time I left you with some work to do, and we have an answer. So that is our answer. I hope you got it well. If you didn't get it well, you can check your working and check your calculations well. So quickly, by the end of this lesson, students should be able to explain the factors affecting molar conductivity. So our factor number one is charge of the ion. Charge of the ion. So we are going to say that molar conductivity is directly proportional to the ionic charge. And the greater the charge, the more strong the ions are attracted. That is towards the electrodes, and the greater the mobility. Remember last time we tried to talk about mobility, that is the speed of the ions. And the faster the ions, the higher the molar conductivity. So, for example, it means, if you look at your screen very well, it means that when we have, for example, sodium and the magnesium and, for example, aluminium, the one which has a higher charge will have greater attraction. Greater what? Attraction. You can even see our values. Magnesium is having a very high value times 2 compared to that one of sodium. Why? Because it has a higher charge. It has a higher charge. And we also say that the larger the size, the greater the mobility. So conductivity increases with the increase in size, or with the larger cations. So the reason is because the smaller the radius of the ion, the greater the charge radius ratio, or we can call it polarizing power. So this leads to attraction of water molecules, and the greater the shell of water molecules, the heavier the atom, and the lower the mobility of the ion in solution, which leads to low molar conductivity. So what do we mean by this? We are trying to say that if the charge is very small, like for example, if you look at our screen very well, we have, for example, lithium. We are comparing lithium to sodium and to potassium. Probably also have cesium down there. So you observe that as you go down the group, size increases. So this lithium has a very small size, or we can say the smallest size. And in this arrangement, potassium will have the biggest size, or biggest radius. So this lithium, the smaller it is, we shall have something we talked about in senior 4. We can call it charge density or polarizing power. Polarizing power is equal to, who remembers, we say it's equal to charge over radius or size. So these cations which have a very small size like lithium, a very small size, will have greater attraction of water molecules. So as they move in the solution, they become very heavy because they are carrying very many water molecules. So as they carry very many water molecules, you'll observe the speed at which they move will be very, very slow. And if the speed is slow, then conductivity is low. So this can be compared to, for example, the vehicles. If you see a vehicle having very many things, normally if you find it in the road, it will move at a very slow speed. Why? Because it is having a big load. But if the vehicle is taking very few things, for example, these small cars, which you can call my cars, those cars, they move at a faster rate. Why? Because they have a very small load. So we are saying here, lithium will have a very high load. So because of that high load, it will move very slowly in solution. Then potassium will have, despite the fact it is big, but its load will be very small. And then to move faster in solution, then we shall have very high molar conductivity. As you see, the molar conductivity of potassium is 73, and that one of lithium is 38. So you see, the one which has a smaller size will have low molar conductivity. Why? Because it attracts very many water molecules, and the movement in solution becomes very difficult. Actually, it drags itself in what? In solution. So it becomes very difficult for it to move, and hence we shall say low molar conductivity. So let's continue. Hope you are following. We are going to talk about also concentration as a factor affecting molar conductivity. So we are going to say that we are going to explain this in terms of strong electrolyte and weak electrolyte. Who can define for us strong electrolyte? So we said a strong electrolyte is a substance or is an electrolyte that fully ionizes in solution. Then weak electrolyte, who can explain to us the definition? Weak electrolytes, we say, are those electrolytes which actually partially dissociate in what? In solution. So you see, we are going to say that as concentration increases, molar conductivity will decrease. Molar conductivity will what? Decrease. So you see our graph, we have represented our explanation in terms of a graph. If you see very well, if you look at this one is for strong electrolyte, and this one is for weak what? Electrolyte. This one is molar conductivity at any concentration. We are going to call this one molar conductivity at infinite dilution. Then we have also here is concentration. Yeah. So this thing, we call it molar conductivity at infinite what? Dilution. If you see this side of our graph, Arrhenius says we can use these two, molar conductivity at any concentration divided by molar conductivity at infinite dilution, to be able to get the degree of what? Dissociation. We are going to use that one in our calculations. So, but actually, if you look at our graph very well, it is extrapolated here. So meaning we extrapolate and be able to get, when this one touches this y-axis, then we can be able to get the degree of the molar conductivity at infinite dilution. Molar conductivity at infinite dilution means that conductivity when we have so much volume of water, when the solution is very, very dilute, very, very dilute. So let's continue with our explanation. So for strong electrolyte, we are going to say molar conductivity for strong electrolytes, molar conductivity for strong electrolytes will decrease with increase in concentration. So for these strong electrolytes, our explanation is going to be like this. Strong what? Electrolyte. Let's summarize it. We say for strong electrolyte. So we say the trend, molar conductivity decreases with increase in concentration. Increase in concentration. Why? So our explanation is going to be like this. We say explanation. So we are going to explain before we look at what we have on our screen. So here we say as concentration increases, we say as concentration increases, as concentration increases, As concentration increases, we say ions come closer to themselves, You know, when concentration is very high, the ions are very close to themselves because we have very little water. So ions come close to themselves. Then we say here, we'll say ionic interference. If you remember ionic interference, interference increases. So the interference between one ion by the other will increase. Then ionic mobility decreases. Ionic mobility decreases. So when the speed of the ions decreases, meaning that even molar conductivity will also decrease. Will also what? Decrease. So that is our explanation, simple explanation. Yeah. So that is, if you see even on our graph, as you see, as the concentration is increasing, molar conductivity is what? Decreasing. So let's look also for weak electrolyte. Weak what? Electrolyte. So for weak electrolyte, we have the same trend. We have the same what? Trend. Weak electrolyte. Weak what? Electrolyte. The trend is the same. Maybe what we can talk about is the explanation. Here you see as concentration increases, a degree of ionization, if you look at your screen, increases. A degree of ionization, a degree of. So here, let's look at our graph again. Yeah. So here we say as concentration increases, as concentration increases, then we say the degree of ionization, we are going to call it, can we call it alpha to make our explanation simple? Degree of what? Ionization. Degree of ionization, this is the degree of what? Ionization decreases. The degree of ionization decreases. The degree of ionization what? Decreases. Then ions present are few. We have few ions what? Present. Then here we say hence. So when the ions are few, we say hence decrease in, let's use this for just to summarize, in molar conductivity. Hence decrease in molar what? Conductivity. That's just to summarize ours. But when you're explaining, you make sure you write them in what? In full. You write them in full. So, you see, we have somewhere different explanation, but the same trend. So even if you look at our graph, you'll observe the one for strong is quite very, very straight, smooth. The one for strong electrolyte is quite what? Very smooth. And the one for weak is a small curve. Small curve. So it shows to you that actually it is weak what? Electrolyte. So let's also talk about dilution. Let's talk about what? Dilution. Dilution may be similar to concentration somehow, but you see, this time we get our solution and then we try to add water. So as we add water, we try to measure the molar what? Conductivity. So you will see the difference in our graphs. Different. So dilution will be, we are going to call it, if you see here on our graph, will be 1/C. 1/C, and this one is for strong electrolyte, and this one is for weak what? Electrolyte. Again, here we have molar conductivity at infinite what? Dilution. Yeah. So again, we are going to say here as dilution increases, the ions become far apart. reducing ionic what? Interference, increasing mobility, which leads to increase in molar conductivity. So here, if we have our factor of dilution, okay, here is actually concentration, this is concentration. And here, concentration, when the solution becomes more concentrated. Then dilution, as you add what? Water. So for dilution, the trends, we are going to say, trend will be, we shall say that molar conductivity, let me try to summarize. Molar conductivity increases. Here we say decreases, here we say molar conductivity increases with increase. With what? Increase in dilution. For both. Then for strong electrolyte, strong what? Electrolyte. If the electrolyte is strong, we say, we're going to try to borrow the same thing here somehow. We say as dilution increases, as you've seen, ions move far apart. They separate, like you see the ions of the molecules of air. Then here we shall say ionic interference. Ionic what? Interference decreases. So because the ions now are far apart, I was giving an example of cars which are in a traffic jam. So when the cars are far apart from each other, we shall have decrease in the jam. Then here we are saying that if the ions are far apart, then we shall have decrease in ionic what? Interference. Then here we say ionic mobility increases. Ionic what? Mobility increases. You see? Therefore, we say then molar conductivity will increase. Yeah. So if you look very well at our graph here, if you go back to our graph, you see here on this graph, we reach a point where the ionization, or we say molar conductivity, becomes constant. If you look at our explanation, a point is reached when the increase in dilution does not affect the values of molar what? Conductivity, i.e. molar conductivity remains constant. This is conductivity at infinite dilution, or we call it conductivity at zero what? Concentration. So there is one when we make a straight line, like we had the other time, the other one was extrapolating, but here we make a straight line, we can get molar conductivity at zero concentration, which is very important when you are carrying out different what? Calculations. Someone may ask, why do you talk about molar conductivity at zero concentration? It is important. It is what? Important. It helps us to get the pH of solution. It helps us to get the number of ions in solution. So that's why we talk about it. And it is shown by our graph. So here again, for weak electrolyte, if our electrolyte is weak, if it is what? Weak. We have a small change in our explanation, very small. Here, we can say as dilution increases, then here we say degree of ionization, degree of ionization, this is actually degree of ionization increases. So ions, you see I'm looking here, ions become many. Become what? Many. Ions become what? Many. Which? So when the ions are many, the conducting ions are many for a weak electrolyte. You say the weak electrolyte, actually, for example, if we have ethanoic what? Acid. It partially ionizes in what? In solution. It partially ionizes in what? In solution. So because it partially ionizes in solution, as degree of ionization increases, more ions are produced. More ions are what? Produced. And when the ions become many, we say molar conductivity. Molar what? Conductivity. Conductivity increases. Molar conductivity what? Increases. Those are the two explanations. You see, when we have dilution, it is like the opposite of concentration. Meaning, as concentration is increasing, dilution is decreasing. As dilution is increasing, concentration is decreasing. So they are opposite themselves. So hope you've got what we've said. If you look at this, we have tried to talk about the Arrhenius equation. Maybe you shall come back to it. If you look at our Arrhenius expression, it's very good to note this Arrhenius what? Expression. Arrhenius expression. So, let's quickly talk about temperature. Let's talk about what? Temperature. Let's talk about temperature. So, the increase in temperature decreases the ionic interactions. So you see, when temperature increases, ionic interference will also decrease. Why? Because when temperature increases, it will separate the ions. It will separate the what? If the ions are close like this and you increase temperature, they will separate. Like you can take an example of boiling. Before the solution starts boiling, but before you will observe that you have some noise. It means that the hydrogen bonds in water have been what? Broken. Even here we are going to say that as temperature decreases or as temperature increases, the intermolecular forces are broken. If we have van der Waals forces. If we have, for example, those other forces you can talk about between positive and negative, they are broken. So as they are broken, we shall have increase in kinetic energy of the ions. And when these ions get kinetic energy, we say they gain mobility. They gain what? Mobility. Hence, this will increase what? Molar conductivity. So we are going to say when temperature increases, ionic interference decreases, ionic mobility increases, hence we shall have increase in the molar conductivity. Then let's also talk about nature of the electrolyte. Nature of the electrolytes. So as you've seen, we have talked about strong electrolyte and weak what? Electrolyte. Normally, strong electrolyte fully ionized in what? In solution. And weak electrolyte partially ionized in the solution. So because strong electrolyte is fully ionized in solution, you'll observe that their values of molar conductivity will be higher. Will always be what? Higher. Why? Because they produce more ions. They don't go slowly, they give more ions, so they will have a higher molar conductivity. Then weak electrolytes, they do it slowly. They do it what? Slowly. So because they are weak, that's why I think the reason we call them weak. So they will give few ions, and then you shall have low values of molar conductivity. Then also let's talk about voltage. At very high voltage, ions move faster. When you connect a high voltage, that is high current, the ions will move what? Faster. Hence, we shall have very high value of molar conductivity. Of molar what? Conductivity. So these are the factors affecting molar conductivity. The first one we've talked about was charge. Second was size. Then we talked about concentration, which is similar, somehow dilution, but there's a difference. Then temperature. Then nature of the electrolyte, and also voltage. You can name even others. Even what? Others. Yeah. So we have an exercise here. Like for example, we are trying to explain why how ionic red dye affects our values of molar what? Conductivity. This time at infinite what? Dilution. You know, values of molar conductivity and infinite dilution are very good to use because they look to be the highest values of any ion. So here they're saying explain why molar conductivity of lithium ion is lower than that of cesium. Hope you can explain that because you've talked about it. Actually, the difference in the size. Here they have even shown you the size. So the one which is small, we said will attract more water molecules. Hence, you'll have a low value of molar what? Conductivity because it is very slow. It is very, very what? So it pulls very many things. You know, in life, like if in life you are pulling very many things, sometimes your rate of development also becomes very slow. But sometimes when you, like let's take an example of cesium now. Cesium here is very big, so it pulls very few water molecules and moves faster compared to lithium. Actually, lithium was supposed to move faster, but the cesium is one which is moving what? Faster. Why? Because probably we can say it has low interference. And then higher what? Mobility. Higher mobility. Then we have another question here. The table below shows the variation of molar conductivity of sodium. So we have here. So this time they have given you the values of molar conductivity and the values of concentration. And they are telling you to plot a graph of molar conductivity against the square root of what? Concentration. So you can plot it very quickly. Make sure you put a title, label the axes, make sure the units are there, and then you draw it. Make sure you even choose a good scale. Yeah. Then explain the shape of the graph. So recognize that sodium hydroxide is actually a strong what? Electrolyte. So we can use our explanation for strong electrolyte to explain the variation of molar conductivity of sodium. Like here, we have with concentration, we can employ this one. As concentration increases, ions become closer to themselves, ionic interference increases like that. Then they say state 2, practical applications of this graph. You said in this graph we can be able to get molar conductivity at infinite dilution, which will help us to calculate, as we are going to do in the next lesson, to calculate the pH, and also to calculate other concentration of hydrogen ions. Thank you very much for following today. Hope you can be able to explain very well the factors affecting molar conductivity. Hope we shall meet next time. God bless you very much.